Hello, this video is on acid anhydrides, and we could equally call them acyl anhydrides, just like in the previous video when we did acyl chlorides. We could have called the acyl chloride acid chloride. They're interchangeable here too, but the more common way that you'll hear this name is acid anhydride. And you'll see from the diagram on the left that an acid anhydride has two carbonyl groups connected by an ester link, and you would have two, usually the same R groups. In this case they're methyl groups, two R groups on either side of either end of the molecule. And that's what an acid anhydride is. We're going to have a look at that in a little bit more detail and name a couple of acid anhydrides before we look at the reactions. And the reactions are very similar to the ones with acyl chlorides. So both acyl chlorides and acid anhydrides, when you react them with water, we're going to get acids, carboxylic acids. When we react them with alcohols, we get esters. And when we react them with either ammonia or amines, we're going to get amides. And in this way, either with acid anhydrides or with acyl chlorides, you can synthesize these molecules. You can add an acyl group of your choice to the nucleophile. So these reactions here are called acylation reactions. Acylation reactions, as were the similar reactions with the acyl chlorides. They're acylation reactions and they add an acyl group. So that's what these reactions do. They add an acyl group right to a nucleophile. Let's just explain what an acyl group is. So an acyl group is this bit of the molecule here that I'm circling around there. So it's the alkyl group plus the carbonyl group. It's called an acyl group. And essentially with all these reactions, we're just adding that bit of the molecule to our nucleophile, which before was water. Was it water or was it ethanol? Ethanol, I think we used. So that's an acylation reaction that is the addition of an acyl group, and in this way we can make all these acids or esters or amides, and in the end, these are often pharmaceutical drugs that we're making. The pharmaceutical drugs are made with these reactions. So that said about the reactions, we're going to just detail each one of those, give you an example of each one of those. And then we're going to compare the acyl chlorides and the acid anhydrides before we have a look at the manufacture of aspirin. So what are acyl acid anhydrides or acyl anhydrides? Well, as we've said on the previous slide, they are groups with an acyl group, two acyl groups linked together with an ester link. And they come from two identical carboxylic acid molecules. We join two identical carboxylic acid molecules together to make the acid anhydride. So let's do one now. Let's take ethanoic acid. So let's draw ethanoic acid out. See page 3. Our acid group. And let's draw the other one. We want two identical molecules, but we're going to draw them upside down, or this one upside down. Draw it like that. You'll see why in a minute. Okay, so you can see there's two molecules of ethanoic acid, and it's a condensation reaction again. So we're going to get, for example, these atoms dropping out, and they're going to make a water molecule. And when they do, and the other bits of the molecules combine together, you get your acid anhydride. So let's just draw that out. We'll make an ester link, like so. and we have our water molecule there that was made on the left hand, and we've made ethanoic anhydride. This is ethanoic anhydride. So there we have it. Now, ethanoic anhydride, how did I name that ethanoic anhydride? That's a good question. Well, if you know the name of the acid that it came from, so here we had 2 molecules of ethanoic acid. We had 2 molecules of ethanoic acid, and all that we did was we switched out the word acid for anhydride. The ethanoic bit is the same, and that's how you name acid anhydrides. So essentially in the acid anhydride you're just looking at this bit of the molecule and assuming you have a hydroxyl group on the alpha carbon. Okay, so that's what acid anhydrides are. Let's have a look at some examples of their reactions. So just like when acyl chlorides reacted with water, we got acids. Well, acid anhydrides, when they react with water, they also produce a carboxylic acid. So let's have a look at an example. Save me drawing it out, save a little bit of time. We've got our ethanoic anhydride molecule here. Let's name it though. It would be made from ethanoic acid because look, we've got 1, 2 carbons. Ethanoic anhydride. That's what we're going to start with, and like the title says, we're going to react it with some water, and then we're going to split it up. It's going to get split up into 2 molecules, and the methyl group is just the same. We've still got a carbonyl bond, but we've got the other bond to our hydroxyl group. So part of the water molecule has linked onto that first carbonyl group, and the same happens for the other part of the carbonyl group, and so you get 2 of these ethanoic acid molecules. Okay, so just to repeat, when an acid anhydride reacts with water, you get 2 ethanoic acid molecules. So we're going to do reactions with alcohols now, and just as with acyl chlorides making esters, we're also going to make some esters here. So there it is. Acid anhydrides react with alcohols, producing an ester. Let's do an example. Let's use the same ethanoic anhydride again, and we're going to react it with some methanol. There's our methanol here, CH3OH, and when we do so, we're going to get an ester. Okay, so let's we're going to get an ester and an acid, in fact. So we've got our CH3 group, and you can see this is coming from the top of the molecule, and we've got a little ester link connected to another CH3 group. Let's just pop in our hydrogens, and there's our ester. This is methyl ethanoate, methyl ethanoate. Okay, so let's just track where the bits of the molecules came from. Let's look at the methanoic acid. This bit of the methanoic acid made this bit of the ester, like so, and this bit of our acid anhydride, our acyl group, made this bit of the ester. There we have it, but we're not finished yet, because look, we've got 2 other bits of molecule to account for, and we can write those out. I'll write them out vertically here. So we've got the CH3 group that was in the anhydride, let's draw our carbonyl group going down, just so that it looks a bit similar to how we drew the reactant. Like so. And in the same way, let's track where the bits of the molecules came from. This bit of the anhydride is the ethanoate, and that makes this bit of the acid, like so. And let's choose a different colour, but we've not done purple. And that remaining hydrogen that was on the alcohol has come over here. So you can see it all matches in the end, like a bit of Lego. So let's name our little bits. So this green bit that ended up over here is our ethanoyl. And this blue, light blue bit that ended up over here is ethanoate. And this is our proton that ended up over here, and this is our deprotonated, this red bit is our deprotonated nucleophile. Right, and you can see it on the other side as well. So that's named pretty much all of the bits. Let's just make sure that we've got this named as an acid. This is ethanoic acid. So in summary, we started off with ethanoic anhydride, which is here, and we made methyl ethanoate and ethanoic acid just by reacting it with methanol. That was our methanol here. The whole thing was methanol. There we go. That looks a bit complicated now, but hopefully you followed it as we went along. Next up is our reaction with ammonia. So acid anhydrides react with ammonia to produce an amide. And let's do a little example again with ethanoic anhydride. Ethanoic anhydride. That's what we're starting off with, and we're going to add some ammonia, which is NH3. Just draw out the displayed formula, and we're going to make an amide, and the amide we're going to make is going to be a 2-carbon amide, because we've got 2 carbons in the half of our anhydride molecule. So that is ethanamide. Right, so let's name it up here. Ethanamide, and that looks like this. We've got 2 carbons, eth, with a carbonyl group coming off one, and the NH2 group coming off at the other side of it, and we just need to complete it by putting in our 3 hydrogens. Okay, and that's our ethyl amide, and as well as an ethyl amide, of course, we're going to get our ethanoic acid with the rest of our ethanoic anhydride molecule. And so let's draw out our ethanoic acid. That's that CH3 group on the left. We've got our carbonyl group, and we've got our hydroxyl group making up the acid. Okay, there it is. And just for completeness, we're going to track the bits of the molecule again. So the ammonia is our nucleophile, and in the process it gets deprotonated with that hydrogen outside the red being the proton concerned, and that ends up over here. like that, and the other hydrogen, let's put it in light blue, the deprotonated hydrogen ends up over here, because it's going to add onto this bit of the anhydride molecule, whereas our acyl group has come over here because that's had the NH2 group added to it. Okay, so there we've tracked our little bits of molecule, and just like with the acyl chlorides, when they react with ammonia, acid anhydrides also produce an amide. So acid anhydrides react with amines. Now it's a very similar reaction to the reaction that we had with ammonia, but this time it's an amine where one of the hydrogens has been replaced by a methyl group, and in this case we then produce a N-substituted amide instead of a normal amide. Okay, so let's start again with our ethanoic anhydride. And this time we're going to react it with our amine. So what amine should we have? It needs to have that group on it to be an amine. Let's make it methylamine. So we've just got a methyl group instead of the third hydrogen. And when we do that, we're going to get N-methylethanamide. Right, so let's draw it out. There's our CH3, our carbon double bond. That's our nitrogen hydrogen and our other methyl group. Just drawing in our hydrogens to make it complete. So we get our N-substituted amide, but we also get an acid molecule as well. For completeness, let's draw out the acid molecule. It's going to be ethanoic acid. And that's our ethanoic acid. And why don't we just track the bits of our molecule as well. But in order to do so, I really need to write out our amine as in a display formula. So let's draw our hydrogens like that and our CH3 group like that. So that's methylamine. Let's name it. Methylamine. And now we can track where our bits of molecule goes. Our methylamine is our nucleophile, and in the process of the reaction it gets deprotonated as a last step, in fact. But so that's what's going to join together with our acyl group. Okay, our acyl group is here. So I've drawn them both in red just now. So let's draw a red bit around here. That's what those two red bits make. And in green, that's our proton, and that gets together with the ethanoic part of our anhydride molecule to make our ethanoic acid, like so. Okay, and so that's the last reaction that we need to do, and you just need to remember that amines, when they react with acid anhydrides, make amides, and substituted amides. Let's just make a comparison of acyl chlorides and acid anhydrides. Let's draw out a generic acyl chloride. So let's do that in blue. So a generic acyl chloride, let's start off with our carbonyl group, and it's going to have a chloride, and let's call this R1. Could be a methyl, could be propyl, could be any alkyl group. And the equivalent acyl anhydride would look like this. Let's do that in purple. Okay, so we're going to have our ester link, all right, and then a carbonyl carbon, two carbonyl groups on either side, and on the other side of the carbonyl group is the same R1 group. Okay, so it's the same R1 group as in the acyl chloride, but in the acid anhydride we've got two of them. And so let's say we're going to react. Let's say we're going to react both with water. So we're going to react both with water and compare those reactions. We're actually going to get the same important product. So with the acyl chloride, you're going to get the acid that looks like this, with an OH replacing the chloride and the same R1 group. But with the acid anhydride, you're going to get that same acid, but you've got the rest of the molecule to worry about as well. So you also get another acid group, which we'll summarize by saying, by writing just like that. So the water was our nucleophile in both cases, and our leaving groups, right, in the case of the acyl chloride was the chloride, in the case of our acid anhydride was this carboxylate ion, and they joined up with the proton from the nucleophile to make the other products, because I should have put HCl in here. Okay, so that's what happened there. And then the acyl groups, which we can ring in green because they're the same. The acyl groups are just the same in both cases, and they went on to make the same acid, which we can draw in a green dotted line around like that. So just looking at the right hand side, our hydrogen that ended up in hydrogen chloride and our hydrogen that ended up on this molecule, this acid molecule, they came from the protons that of the nucleophile, and the rest of the secondary product was the leaving group, and this was the leaving group from the acid anhydride. And the last thing to say is that, here is that we chose water to make the reaction with, and it just remains to say that if you'd have chosen the other nucleophiles, you would have got the same pattern. Lastly, let's talk about the manufacture of aspirin, and as well as aspirin, lots of pharmaceutical drugs are made in this way with this reaction mechanism. And aspirin is an ester. So an aspirin is an ester, and you know how to make an ester with this reaction mechanism. You take your acid anhydride or your acyl chloride, and you react it with an alcohol. Right, the alcohol concerned here is actually salicylic acid, and that might confuse you for a bit until you see the structure of salicylic acid. So let's draw it out. Salicylic acid is actually benzene ring with a hydroxyl group, and that's the hydroxyl group that takes part in the reaction. It's also got an acid group like so. So that is salicylic acid. Salicylic acid. But it functions as an alcohol as far as this reaction is concerned, because it's got that extra hydroxyl group hanging off the number 2 carbon of the benzyl group. Now you could react that salicylic acid with either the acyl chloride or the acid anhydride. But in industry, it's mostly the acid anhydride that's preferred, and that's the reason is because, one, it's cheaper. The anhydrides are cheaper than the ethanol chloride, for example. It's also safer to use, no hydrogen chloride coming off, and it makes it less corrosive, and it reacts more slowly, so that it's easier to control. Okay, so we're going to do it the same way as in industry, and we can react it with the acyl chloride, and in fact it's ethanoic anhydride. Sorry, we're going to react it with our acid anhydride, and the one we're going to use is ethanoic anhydride. We're familiar with this by now, ethanoic anhydride. And you can all draw this out by now. CH3 and another CH3 group here. Okay, so that's our ethanoic anhydride, and let's draw our reactants down here, our products rather. So the ester that is made in that reaction is aspirin, and aspirin looks like this. It's got the benzyl group, and it's still got the acid group attached to the top of the benzyl group. But the hydroxyl group has changed into an ester link, and then we've got the rest of our nucleophile, which is drawn out as such, and our secondary product is the acid, as usual, ethanoic acid in this case. So let's draw our ethanoic acid. That's our ethanoic acid. Why don't we just go ahead and name, this is our aspirin, and this is our ethanoic acid. Okay, now what we probably want to do is we want to track all the bits of molecules to see how we've created our products. This is an acylation reaction, remember, acylation reaction, which is the addition of an acyl group to a deprotonated nucleophile, and this is our acyl group that we're going to add, and this is our deprotonated nucleophile, and that makes our aspirin, like so, and that leaves our carboxylate ion, in this case ethanoate. Let's draw that in light blue to get together with the proton and make our secondary product, which in this case is our ethanoic acid, like so. Okay, so there we have it. That's how to make aspirin, and we might do that in class. Okay, as usual, let's finish off by making sure that we covered off everything we wanted to do. What are acid anhydrides? I guess we know that by now. Made from two identical carboxylic acids, got two carbonyl groups linked with an ester link. Okay, reactions with water, alcohols, ammonia and amines, and I think we should remember by now what products we get from each of those nucleophiles. And then we did a quick comparison of the acyl chlorides and acid anhydrides, and we noticed that we got the same main product, whichever way we used. And we mentioned when we were talking about manufacture of aspirin that in industry it's usually the acid anhydride that's used to acylate a nucleophile because of cost and control reasons, and safety reasons too. All right, so that covers the other learning objectives as well. Hopefully that's been interesting.